on stable hatching. Here we will look at the mathematics of stable hatching. Okay, Dr. Professor Sushmita will tell you more in detail. So I invite her to the first talk. Thank you.
Can you all see all aspects of the screen? If there is something missing because of font, color or whatever, please, and I have used some screenshots from a textbook and so on, so just let me know if you can't read something, okay, because the details are sort of important here. Yes. So the protocol for these talks is to ask a lot of questions, okay. So you just raise your hand, or if you have something you can just sort of speak up. Don't wait for the end of the talk to so on, because I think questions are most relevant or interesting in the moment, right? You don't want to wait for the end of the talk to ask. Moreover, this is not the only, we'll be around, there will be a discussion and problem solving session where I will be there and others will be there as well. So please feel free to come up and ask. Okay, so as I said today, this first talk will be about broadly stable matching and the mathematical foundations of stable matching. In particular, it will be about the two-sided market setting, also known as the bipartite graph setting. So the plan is to revisit the Gale-Shapley algorithm and deduce some important sort of properties from it. So if we look at the same Gale-Shapley algorithm as we have known, but just looking at it from a slightly different perspective, doing a little bit more bookkeeping allows us to sort of use it to go further forward. So there's this notion, so as I said that we'll be talking about some more additional properties of Gale-Shapley, and that's where the shortlist and its properties come in. That leads us to some properties of stable matching itself that remain in the background when you're just running the Gale-Shapley algorithm, but basically which build up the entire framework of the mathematics of stable matching. And we learn about a very important object in the world of stable matching called rotations, which are really the machinery behind this whole lot of work that has happened in the last many decades, like 40 years and so on, in stable matching. So, after that, we'll basically connect some dots and see where the lay of the land is. Okay, so that sort of a thing. So the talk may seem a bit meandering and lots of definitions and so on and so forth, but I'm going to try to make the definition like stack up one after the other. So there should be a connection between what I've said before to what I'm going to say next. If you lose that connection, please ask. Okay, why? If you feel like why are we suddenly talking about this and that, please pause and ask me. At least the context and this much of the framework should be very clear at the end of this. Is there a bit of an echo? I feel like I'm hearing my voice twice. Are you people hearing me clearly? I think, okay, I'm going to keep it then. Okay, so these are the two gentlemen, David Gale and Lloyd Shaw. I really like this picture. So, I mean, it's hand drawn and so on. I think oil painting. So, let's look at, do you all know the Gale-Shapley algorithm? That was part of the prerequisite. Pallavi said, no, they have to know the Gale-Shapley algorithm, else much of the time would be spent just talking about that. Okay, so we will talk about a version of the Gale-Shapley algorithm. Let's look at the pseudocode and let's see if there is anything different here. Okay, so first what we do is you have man on one side, woman on the other side. Okay. I must start with apologies. The stable marriage terminology and all the associated terminologies came upon in the 1960s. Some of this terminologies and nomenclature may seem very dated to you today. It does to me as well. Apologies, because lots of textbooks, papers have been written about this, and until people really start complaining, we are going to stick to that. And at some point in the future, things will get rewritten, I assure you, the thing is coming. But so far I might switch between marriage and matching. I tend to not do, but still, okay. But more than that, there will be this man-woman type thing, men proposing, women rejecting, and so on. So please bear with me. So each at the So at the beginning, everybody is free, right? This is the male proposing version of Gale Shapley. The men are proposing, the women are sort of processing the proposals, and they are deciding how to sort of accept or reject right away, and so on. So at the very beginning, W is the first woman on the man M's list. So M is thinking of proposing to W, and it does so. Then currently, if W is engaged to some other man P, W basically rejects P and accepts the proposal from M, okay. And then for each successor M prime of M on W's list, so what does this mean? So W basically now looks at its preference list, and she sees all those people who are ranked less than M on her preference list, they are automatically rejected, okay. So she removes them from the preference list, and that automatically triggers a change in those men's preference list. They also have to drop W from their preference list, remember. So we can only match people who have each other in their preference lists. That's a very important property that we have in matching. That's why it's even matching. That's why we are talking about edges and so on and so forth, right? Okay. So is the pseudocode, and then basically you delete. So woman deletes these men M prime from her preference list who are ranked less than M, and basically that means delete the pair M prime W, or delete the edge M prime W. So is the pseudocode clear? So at the way the pseudocode is written right now, at the very beginning of the algorithm, M is there in the preference list and W is M's top choice. So it says that currently if W already is matched to somebody, at the very first nobody is matched to anybody, right? So that condition will not be triggered. But as the first proposal goes through, because none of the women are matched to anybody, and after that the women basically start like pruning their list, removing things from the suffix, and that leads to that trigger in the men's preference list. They start dropping the women who have already dropped them from their preference list. So is this exactly is this the Gale Shapley that you are familiar with, or is there something different? How is it different?
So they were not looking whether P is ranked above P or not.
They were not?
Here we are not considering whether P is ranked above him or not.
Yeah, that's a subtle difference. See, does it say anything? The moment W sees it, I am matched to somebody, but a new proposal has come, it automatically leads to a sort of a break in that engagement, and M is accepted by W. That's probably not the type of Gale Shapley that you have seen. The standard version is you look at the proposal that you are holding and the proposal that has come to you, and you compare which is better, and you dispense off with the one that is not the better one, right? So if we are not going to compare our current partners to the proposal that is coming through, then how do we ensure stability?
Actually, what is happening is that if some W is in some list, and we are saying that like my W, like let's say W1 as a woman is there, and what happened is that we have a, let's say some matching happened to P, then all the man list below that the P preference is already removed. So if whenever there is some matching possible, then it will be always be a higher preference, not lower preference. So in the end, result will be same, but
Right. So what we are doing here is we are keeping an invariant. At the loop invariant here is whoever is there in the women's preference list is at least is the current partner, her current partner, obviously she is there in her preference list, and all other men whom she likes better than her current partner. From the on the men's preference list, right, because of the trigger change and so on, symmetric notion of how things are being dropped is that the men currently hold at the top of their preference list is the woman that they are currently matched and they like the most among those that are available, and women who are ranked less than this woman but who like him more than their current partners. This is why the moment this man proposes to a woman, W, by that property alone, M being present in W's preference list means he is better than her current partner who happens to be P. So this is the additional bookkeeping we are doing. This we are only keeping partners from the women's side who are better than their current partner, and from the men's side only those women who are less than ranked less than lower than their current partner. Okay. So whenever, this is why whenever a proposal comes through, it's a default accept. Okay. So this is what we call extended Gale-shaped lay. Why do we call extended Gale-shaped lay? Because this allows us to basically, okay, you could have called it something else, but what we are trying to do here is basically prune the preference list as we go along. And by pruning, I mean we drop redundant partners who can never be sort of part of a stable matching. Now that may not be obvious right now, but we will see a result of that kind. Okay. So the encoded within the algorithm is this property that we are only keeping partners who could be matched as part of a stable matching. Okay. So that's what we call a short list. The original preference list is pruned step by step. The men are sort of dropping people from the top of the preference list, they are pruning the prefix, the women are pruning the suffix, right. So that's how the operation is going on. So, formally stated, you remove man M from W's list and W from M's list if W's current partner is better than M. This is the necessary and sufficient condition to capture that loop invariant. Now let us try to see how this whole thing impacts the algorithm as we go along. So this is bunch of 8 men, 8 women, and they are the rank preferences. So in man 1's preferences, I think you can read. Are all the letters clear? They are very colorful, but I hope you can read. That's the more important thing. You have a question? Yes.
What is the estimated improvement in terms of time complexity that the extended has over the long?
None. In the worst case, it will still be the same thing as a normal Gale-shaped lay, because it might be the preferences are such that you are not really dropping anybody. It's everybody. Think about the men's preference list in one order and the women's preference list in the other order. Everybody still has to go through order n square operations, order n square proposals.
So what is the benefit of using this algorithm?
The structural properties that it gives. That's why I was saying at the beginning that we look at Gale-shaped lay but in a different light, slightly more, and that allows us to infer some properties that we will be talking about. That takes us further. It's not the improvement in the time complexity, but what we can sort of glean from what Gale-shaped lay is doing. Okay. So if you run it, so the mu0 is basically the man optimal. So if you can't read the exact matching, does not matter, but the point is that there are several stable matchings here. The first one, this is the man optimal stable matching. Man optimal stable matching is among the set of stable matching, the stable matching that outcome. Okay. And there are, I believe, 6. Okay. So mu5 is the woman optimal stable matching. Okay. All right. So now let's see, these are the stable matching, but let's see how this whole thing works. Okay. So I'm just going to do it briefly so that you can see. So currently, suppose we start with mu0, which is the man optimal stable matching. Okay. So so the way that our algorithm was described, it would have stopped at the man optimal stable matching. What extended Gale-Shipley allows us to do is, now you start with the man optimal stable matching and find the next stable matching by this pruning thing. Then again start from there, you can go on to the second stable. That's why extended Gale-Shipley. It's not a one-step process. You can sort of continue it further forward. So the first M1 is matched to W5, M2 is matched to W3. So the square boxes, blue boxes are basically indicating who my current partner is. Now have a proper look at this, okay. You will see, okay. So now in this picture you will see, okay, M1 is very lucky, it's currently matched to the top person in his preference list. M2, not so lucky, is matched to the second person in the preference list. So what that means is his top preference, which is W2, currently holds a better sort of a partner than M2, and therefore in W2's preference list we strike out M2. And in fact, if you go through W2's preference list and the men's preference list, you will see that W2 in this matching being matched to, who is it, M7, right? This thing. Okay, I think, is the, this thing is not visible, right? This one. So the M7 W2. So it means all these people who are ranked below M7, M2, M1, M4, they are struck from her preference list and so on. So if you see this, it should tell you that, so the ones that are struck out, imagine as if they don't exist. So after the prune list, you know that for the men's preference side, the current partner is at the top of the list, and from the women's side, the current partner is at the end of her preference list, okay. So that's the outcome here. So the cross marks basically show that they have been dropped from the women's preference list. So the men also have to drop them wherever they are in their preference list. So while we cull from the top of the men's preference list, but drops can happen anywhere else also, okay. So that's the thing. So ultimately what happens is we get a preference list, which like a profile which is this much smaller. So nobody still has all of the partners. Everybody's preference list has dropped from 8 to 6. No one's bigger than M5, right? M5 and W5. Okay. And you get the underlined individuals are the current match partners. So now if starting here, if I again start Gale-Shapley again using the same thing, we will basically get to the next preference, next stable matching. What is next? It's not clear, but we will get to some other stable matching because of the same property as before. If Gale-Shapley, the normal extended Gale-Shapley one-step process gave you a stable matching, the same should happen here also, right? Okay. Now, so let's recap some of the properties that this algorithm actually gives us, that the normal Gale-Shapley does not necessarily, at least it's not obvious, you kind of have to argue separately and so on. So the first and foremost is that all stable matchings, and okay, the list that we form like that, the shortened list, is what we call the GS lists, okay, the Gale-Shapley list. So all stable matchings are contained in the Gale-Shapley list. Now an important question here would be, the culling was done from the way that the men were proposing. The same thing can happen if the women propose. So if you do it from both sides, you would get possibly even a smaller shortened, shortened preference profile. And all stable matchings are basically contained within this shortened profile. That's what this first condition is saying. Now, no matching contained in the GS list can be blocked by a pair that is not in the GS lists. Is this property clear? Is it obvious to you? Why? You want to answer?
Because the shortened list has only the stable matching, so any pair outside those things cannot block the stable matching.
Okay, suppose you didn't know the first condition, that all the stable matchings are, all potential stable matchings are there in the GS lists. can you still prove condition 2? So I didn't actually say this, but everybody knows what a definition of stable matching is, right? We need to have a mental memory of what a stable matching is, that there are no blocking pairs. Blocking pairs are partners, like are man and woman pairs who are in each other's preference lists, and they prefer each other to whoever their current partner is. That's a blocking pair. If you don't have a blocking pair with respect to the given matching, then the matching is stable. Okay? So use that definition. So if you think in terms of who are not in the GS lists, if the woman is not present in a man's preference list, it is because that woman got a strictly better partner, right? And so if there is an edge that is not in the GS list, for it to block a matching that is actually present in the GS list, it means that both of them should prefer each other to whoever their match outcome is from the GS list. That is obviously not true by our pruning criteria, that you drop only when you get a strictly better partner. Okay. Now, in the man optimal stable matching, each man is partnered by the first woman on his GS list. Okay, this is exactly what we saw. This is by construction, right? So the third property is rather straightforward. So is it clear? So what I am trying to get to is for you to have a mental picture of how man optimal stable matching is one extreme solution and the woman optimal stable matching is another extreme solution, and all the stable matching somehow lie in between. Okay, so that's the sort of this viewpoint that we are trying to get to. Now there are so many different and interesting properties of stable matching. There's just too numerous. People keep finding more and more things and so on, and rediscovering lots of properties that were known before by new and interesting ideas. So I'm just going to say a few that might be the easiest to remember and will help us sort of during this discussion. So if you have two stable matchings M and M prime, and so you have, suppose M has a N, M and W are partners in one stable matching but not the other. Okay? In that case, one of them will prefer M and the other one will prefer M prime. Is it clear what I am trying to say? You have two stable matchings M and M prime, and you have a pair M and W, a man and a woman. They are matched in one of the stable matchings, let us say M, but not in M prime. So what we are saying is, if M prefers, because they are not matched to each other in M prime, they obviously have either a different partner or no partner and so on and so forth, right. So they can rank, they can compare M with M prime. Both of them will be able to compare M because the outcomes are different. If they had the exact same partner, then they would be indifferent, right. So with that in mind, we say that if M prefers this matching, man M prefers the matching M, so there is too many M's going around, I am going to say mu and mu prime. So if the man M prefers the matching mu, then the woman prefers mu prime and vice versa. So what does this tell us then? Can you draw some conclusions from it? It's this property that actually allows us to show that a stable matching is always popular. The notion of popularity I spoke about beginning, that you will all, if whenever we have two stable matchings, each one is equally popular. Each one is preferred by exactly the same number of people. So there is no other stable matching or any other matching which is strictly, hold on, there is no other stable matching which is more popular than this stable matching. At least this result says this. Now the question is, why can't there be an unstable matching which is still more popular than these stable matchings? That still remains to be seen, and we can talk about that later, but is that clear? That at least this one says this. Yes, you were saying something? Okay. Alright. Now this is, okay, so now if there's a notion of, so as I was saying, there are two extreme matching, the man optimal stable matching and the woman optimal stable matching. All the matchings in between, all the other matchings are sort of in between. What does in between mean? So that it's not that any two matchings are comparable. It's not always the case that you can look at two matchings and say, oh, this is at least as good for every man as this one is, okay? But sometimes you can. This sort of property where some pairs of things are comparable while others may not be is what we call the partial ordering. So this is what this partial ordering is. So when we say mu dominates mu prime from the man's point of view, it means that every man either has the exact same partner in mu and mu prime or has a strictly better partner in mu. Is that clear? Okay. So if mu dominates mu prime from the man's point of view, then it must be the case that the opposite happens from the woman's point of view. Is this clear why this should be true? So if one direction, like they're symmetric, right? If you can prove one direction, the other is sort of the same thing, same argument. Why is this true?
It's better for one side because bipartisan inherently means that if you look from the other perspective, it has to be better for the other.
Why? What does bipartition have to do with this?
Because here it's ordered, right? It's an increasing order. It's never that like you have two partners and you can say, okay, they're of equal preference to me. So because it's always discretely different, every single partner has a discretely different preference.
Not necessarily. You can have multiple people with the exact same. Are you saying that the preference lists are somehow distinct?
No, in the preference list itself, every single partner has at least a little bit of difference from each other, right? So even partner 1 and partner 2, you can say I prefer partner 1 over partner 2.
Oh, you are saying the preference lists are strictly ordered.
Yeah.
That's true.
So because of that, if one particular list has an order that is preferred to one sex than for the other, in M prime it's obviously better.
I don't see an argument purely based on what you are saying, but this follows from the first theorem, that when you have two matchings mu and mu prime, if mu is dominating mu prime, it means every single man for any given man, he either has the exact same partner in mu and mu prime, or he has a strictly better partner in mu than mu prime. What does that mean? That means that his partner in mu prefers mu prime over mu. It's this exact same thing, right? So if mu dominates mu prime from the men's perspective, then mu prime must dominate mu from the women's perspective. It's just one line application of the above result. Yes.
We have a matching that gives exact same result from men's point of view and women's point of view.
What do you mean exact same result from?
Exact same pairing.
So a matching, I don't quite follow. So you're saying the man optimal stable matching is also the woman optimal stable matching? Yes, of course. There are instances that happen, that there is exactly a unique stable matching in the instance. That happens, yes. Okay. And finally, so you take, this is one of those remarkable properties of the stable matching problem. Taking any two stable matchings, any arbitrary stable matchings, for each man, give him the better of the two outcomes he gets between the two matching mu and mu prime. Okay? What you get is this matching. This is called this. I don't think this is working. I have a pen here. I'm going to mark this. Yes. Okay. So this. How do I erase this? No. Sorry. This is the way to erase it? No. It's just saving. Yes. Okay. Okay. This is each man. Can you read my handwriting? Okay. So I'm saying that this is called the meet operation. So for every man you see, if he gets the better partner in mu or mu prime, whoever is the better one, give it to him. If he has the exact same partner, then there are no choices to be made. This is the opposite, where you give each man the lesser of the two partners. Is there, just by this operation, if I tell you, is it obvious to you why these objects, the resulting objects, should even be a matching, let alone a stable matching? Why aren't two men in conflict with the same woman, like, you know, trying to get the same partner? Think about this, okay? This is one exercise. Please try to work this out. Why this operation actually results in a matching, and that to a stable matching. When you have a partial ordering with this sort of property, this join and meet operations defined, we have what we call a distributive lattice. Distributive lattices are very interesting objects. They have this maximal element and a minimal element, and of course the elements in between can have a sort of respect the partial ordering. So in this case, the partial ordering we are talking about is the dominance relation. Now what exactly is formally a partial ordering, we will see little later. So by now you can just think intuitively what we mean, and that's more than enough, is that not every two matchings are comparable, in the sense that not every like if I look at the preferences of every man, if I compare mu and mu prime, it's not always the case that every man has at least a good partner, as much a good partner in mu as he does in mu prime. If that is the case, then we say mu dominates mu prime. Otherwise, if this does not happen, we say they are incomparable. Okay. All right. So, and finally, this in a stable marriage instance that allows unacceptable partners. So, for example, the standard Gale-Shapley says rank everybody on the other side of the preference, on the other side of the market, right? This is not necessary. Suppose you have, so that would result in a complete bipartite graph. Suppose you don't have a complete bipartite graph, you have an incomplete bipartite graph, some edges are missing. In that case, can you tell me what should be the size of the stable matching? Okay, if the preferences are complete, what should be the size of the stable matching? It's perfect. Basically, it's everybody gets a match partner. But if you have incomplete preference list, the size of the stable matching can be significantly smaller. Okay, so that's the thing. And in fact, we can say that the set of people who get matched in any stable matching is always the same for any given instance. So this is what is, what is the time, this thing? Okay, so I'm running a little late, so I'm just going to move along. Okay, so this is also an interesting property you can try and show. This is not going to go away? Okay, all right. Okay, so let's talk about some of the questions really. Why are we even talking about the mathematics of stable matching? This slide probably should have come at the beginning, but it's just as well before we delve deeper. Let's talk about why are we even talking about the mathematics? Why didn't we just end it? Because understanding the properties of stable matching allows us to do much more than just find one stable matching. In particular, it allows us to enumerate stable matchings. Now, do you know in a given instance how many stable matchings can there be? Any idea? Okay, if I gave you a complete bipartite graph, how many matchings can there be? If I didn't talk about stability, just matchings. Yes, exactly, n factorial, right? It's like counting number of one-to-one pairs and blah blah blah, all those things, correct. A stable matching, and this was known fairly early on, it can rather easily be shown can have exponential number of solutions, meaning a given instance of stable matching can have as much as 2 power n number of solutions, okay, 2 power n number of stable matchings. So, we can't possibly enumerate these stable matchings in polynomial time because they are just too many. So, but enumeration is still a very important question, it is an interesting question, and we always ask about what it means to fast enumerate a set of solutions, for instance. So, what that means is, can you enumerate the solutions with there are two notions, that with polynomial delay, meaning you give out m1 followed by m2, m3 and so on, and between each such steps you basically spend polynomial amount of time. This would be considered a very efficient enumeration. The other one is overall you take time complexity. Now, it may not be that between step 1 and step 2 you are always spending polynomial time, maybe certain steps require a lot more time than polynomial, but however overall you are going to spend something which is dependent on the size, the number of solution times some polynomial function. That would also be a fast enumeration. So, in this case, understanding the properties of the stable matching, the mathematics of it, we can actually enumerate rather quickly. This distributive lattice structure, just by looking at Gale-Shapley, that one algorithm which gives me man optimal stable matching or the woman optimal stable matching, we have no idea what the other stable matchings are like. But understanding the structural properties allows us to very clearly place every stable matching in a very meaningful way in relation to the other stable matchings. So, that allows us to do search, and as I said that sometimes we just do not want any stable matching, we want a stable matching with additional properties like fairness or maximizing, minimizing some other objective criteria. Then knowing these structures helps us in doing search fast. Okay. Yes, a long open question was giving an upper bound on the number of stable matchings. Like I said, the lower bound was well known, for decades, but the upper bound up until recently, up until 2018, was as best as n factorial. So, 2 power n and n factorial, like you can see as this chasm of difference, right? And people worked for decades to push it down, like either tighten the lower bound or push down the upper bound and so on. And it was in 2018, it's a just beautiful paper, it came out in STOCK. STOCK is the preeminent theory conference. It was shown that it's actually c power n, where c is some constant. They didn't optimize the c, but it's not n factorial, it's actually an exponential function in n. Okay, that was also done by understanding the mathematical object we'll talk about next. And of course, I already said it, and Pallavi will actually talk about this, one of such fairness notions, egalitarian stable matching, in the afternoon talks. Okay. Okay. So I think with that, this is over, right? Yes. So this is a perfect timing. So now I'll leave you all with a cliffhanger. What's to come next? We'll look at the gear, the object that makes all of this possible, this thing called rotations, and we'll literally just sort of delve deeper and see how this object rotation, which I'm going to define, of course, helps us in addressing all these questions. Okay, so I'll see you in a bit.